you want me to start?
So it means it's, yeah, a bit laggy. So yeah, start.
Okay.
Get this.
So the paper is called Learning Deep Features for One-Class Classification. And basically this paper is important because many of the classification methods that we use in deep-based convolutional neural networks are designed for binary or multi-class classification. So a binary classification means that you're classifying between two possible classes, and a multi-class extends beyond just two. However, this particular paper is actually addressing what would be called unary classification. That is that you're classifying a single class. And what that means is that you want to know whether a particular set of objects is of a class A, where A is the thing that you care about, or anything else, which could be basically anything. And that actually ends up being quite a complex problem, because one simple way of sort of looking at this unary classification is you might just think, oh, suppose I just take the class I care about and stick it as class A, and then everything that is not that class, stick it in class B, and then I get binary classification again. But that doesn't work so well, because binary, if you do that, often what happens is that the things that are not that class is loads and loads of things, which have a lot more examples, you have a lot more data, and you may also end up being imbalanced. And so that means when you end up training, your system may be biased towards things that are not that thing that you care about. And so you don't get a good sort of balance between the classes anymore. They become a very imbalanced classification system. So this system
is different when you say multiple classes. The handwriting example, is that all the same class, or is that multiple classes?
In the handwriting example, which is called MNIST, is basically it has 10 different digits. And in that particular case, it's a multi-class classification problem because there are 10 classes from 0, 1, 2, 3, all the way to 9. The unique thing about this is that you're able to sort of deal with the thing that, say for example, just the zeros. You have images of zeros, and then you have images of every possible other thing, like cats, dogs, sky, bones, anything. But you just want to be able to accurately identify the things that are in fact zeros. Yeah. And so this has like a relationship to things like anomaly detection, doing things like, it has a couple of applications that it mentions at the end of the paper. So we'll just go through the main thing right now. So in the introduction it says that one-class classification has received considerable attention. And the objective is to recognize instances of a concept by only using the examples of the same concept. So they have an example. They have a picture on the right-hand side there with normal chairs and classified between abnormal, normal, and normal. And one-class classification is encountered in many real-world computer vision applications, including novelty detection, anomaly detection, medical imaging, mobile active authentication. In all these applications, the unavailability of samples from alien classes is either due to the openness of the problem or due to high costs associated in acquiring samples of such classes. And so that is another sort of relationship as well. And this is what we usually call an open set problem, whereas many classification algorithms have the assumption that you're in a closed world where you just know that everything is of one or these other classes, and they're all one balanced between each other. And then basically it talks about a couple different sort of papers that have introduced different possibilities of doing this. On the third paragraph it says, despite its importance, contemporary one-class classification schemes trained solely on the given concept have failed to produce promising results in real-world data sets. For example, one of these papers has achieved an area under curve with a range of 60 to 65% for the CFAR10 data set. And that's a data set of 10 by 10 square images of basically small objects of sorts like planes, people, whatever else.
10 pixels or 10?
Oh, yeah, the 10 classes, but I actually think they're also 10 by 10, or maybe.
That would be really pretty small.
Okay, maybe not 10 by 10. The 10 classes of different images. They're color. That's a color 10 class image, but the images may. I remember the square images are quite small though. And then, however, as we note, the computer vision is a field rich with labeled datasets of different domains. In this work of the spirit of transfer learning, we step aside from the conventional one-class classification protocol and investigate how data from different domain can be used to solve the one-class classification problem. And they call this the specific problem the one-class transfer learning and address it in engineering deep feature targeting one-class classification tasks. So the actual solution presented in this paper does make use of transfer learning, what might be called mini batches. The batch, like actually having multiple sort of images is important. It also has sort of relationships with things like Siamese networks where there's like multiple kinds of things that, multiple different clones of the network operating in parallel. Yeah, we'll see how that all ends up working.
What's the definition of transfer learning?
So transfer learning is where you take the weights of a pre-trained network, you copy it over to a new network or a model architecture in the hopes that because the weights that you acquired, that you copied over, that means they can be reused for your new classification task or new data set with minimal training required, or minimal further training required. So the weights are sort of like, how much of you guys are aware of how neural network actually trains or learns? Anybody doesn't know?
I don't know. Explain, please.
Yeah. Well, actually, this is a really good question because I've been writing a book about this.
One or two.
We're gonna what?
I've been writing a book about it. Just the plug whoever.
Yeah.
But anyway, so.
Should we turn the camera too?
Yes, please. But if you don't, if you can drop, you might drop it though.
We
How did you know?
I can predict the future. A neural network is well trained.
Maybe you see the stat before he knows the stat describe.
Yeah, transfer learning is being basically the one of the big sort of. I think that's upside down. Yeah, just sort of twist it around.
Very true.
So basically, so neural network go all the way back to like the 1960s when this guy, I can't remember his name, but he invented the perceptual system. And the basic idea is that suppose you have a function. Try to find
Hey, the lighting is not so good, yeah, Roger.
Yeah, there's not good lighting in this one. I'll just try and use it.
We don't have a mobile phone.
It's expecting us to be here in the middle of the day.
Yeah. Suppose you have a function f, which is applied onto various different x's. So in this particular case, what you have is you have two x's, each representing a feature of your problem, whatever you're trying to model. So for example, if, this was sort of like, you were to go out into the real world and you basically observe the real world and then use instruments to measure something. Maybe it's like the height of people, and maybe this is the color of the skin, right? And you just basically put down points on every single one of them, and you get all these sort of points, and you get a scatter plot basically. So then the height and whatever else, that's your x and x2. Then the y basically is your other feature, this sort of hidden feature that you don't know about, or you sort of do know about, but you don't want the model to know about it ahead of time. You want the model to learn the relationship between these features to this output feature. Now, in order to do that, perceptrons and similar other kinds of algorithms are considered supervised machine learning systems. What that means is that you actually have to go out to the real world and actually get this third access of data, because you need to use it as sort of answers that can basically tell whether your model is getting it wrong or getting it more correct, and then fiddle with the model parameters until it gets it closer to correctness. Just like basically giving the answers to an exam to a person who's training to pass the exam. So the guy who invented perceptron basically took this idea. You have this function here, and he basically said that for the purpose of classification, there's this function called the step function, like that. And then basically at this point there's 0, and so if the output y is above 0, positive, then the output of this activation function will also be 1, and if this is negative, then it becomes 0. So we call this activation function it could just be g, for example. In this case, it could be the step function, the step function, which in this case should be something like 0 if the h is greater or equal to 0 else 1, or it could be another, right? It could be 1 as well. And so the perception.
So what's that doing?
Sorry?
I guess again, it's just spinning you, but that's the neuron firing, perceptron firing. You've got to.
Yeah, I just want to get to that first. First, like, there's a lot of sort of mathematical concepts that just came from lots of different places, and people just sort of put it together. So this is the step function, which is just a function that basically says if your x is above 0, it's going to give you 1. If it's below 0, 0.
Is it deciding really something?
Hold on, we haven't got to that. It's just a mathematical function. Nothing special about it. Yeah. So the guy who invented perceptron just basically put these two together, and all he said. Firstly, he didn't convention-wise. We don't call this f. We actually call this h, because it means hypothesis. It's like your hypothesis of x1, x2 to your output, and basically the perceptron function p is equal to g dot f. Sorry, h. G dot h. So h happens first, then you apply the g, and you get back a 1 or 0, right? And that basically gives you a model that can perform binary classification, because you put in whatever features you want, and you plug it in through these things, and you get back a 1 or 0, right? That's a binary classification system. So then what we need to do is derive this h. We don't necessarily need to derive this. This is fixed. The step function, there's nothing to really derive, except for what we might call the threshold here. This is like if it's greater than 0, so you're basically just moving the step function left to right in a way. But generally we don't do that. We just leave it as it is. So the only thing we do need to sort of fiddle with is the h function, because the h function is what takes x1, x2 to y. So as I mentioned previously with the supervised method, as you basically pass your data set, so if you've got like, let's say you've put your data set into, I don't know, like a CSV Excel table, and then you have your x1 here, x2 here, and then you have your y being the output that you want the model to learn, and you got all these numbers, like that. And what you sort of do is you sort of like just take those x1 and x2 and you just pass it through a h, a possible h. So what is a potential h? Well, h could be really anything, but they took the most simplest concept of h, which is what we call a linear combination. And that's basically just simply something like this. H is equal, suppose we'll take x1, x2, it's just simply equal to a coefficient of 1 multiplied upon x1 plus the coefficient of 2 multiplied upon x2. And then usually there is one more coefficient 3, applied onto just 1. And this is called the bias. And that is the most likely the simplest possible function that could take this.
So it's what you call an affine function. So it's if you didn't have the constant, it'd be linear, but you've added a constant term. So it just offsets it off from the origin.
Yeah.
Alternatively, you said let it be polynomial, but no terms beyond order 1.
Right. Yeah. So then, what's interesting about this function is that now you have the things that you can actually sort of play around with is the coefficients. This one. So there's two coefficients. And in machine learning world, we call these weights. So weight 1, weight 2, and then the bias. Right? So imagine like the simplest possible combination of x1 and x2 is simply set the weight 1 to be 0, weight 2 to be 0, this one to be 0. 0 plus 0 plus 0 equals 0. That's not very right because if we get results like 4, 5, 9, 10, whatever it is.
Are you going to talk about the biological inspiration?
No, because I'm not actually familiar with the biological.
Just very quickly, like, because it's very high level, and neuroscientists will say sort of yes, but also sort of no. But you know, basically about a neuron is it fires, so it is kind of a binary thing at a rough level. Like, there's all kinds of other things, but that's what the activation function is measuring.
Yeah.
Either happens or it doesn't. And then the neuron, you've got all these synapses between them. So it's things. There's a learning process, which means the synapses adjust. So that's what the weights and what are changing. So it's a roughly linear thing. So if it's fired before the weights adjust, so that's a very crude mathematical model of yourself.
Yeah. So like from my understanding in the neuroscience world, they describe these things because they study the brains, and then some computer scientists sort of just saw a potential approximation of that. And they just sort of say, oh, what if we take a step function and we take a linear combination? That seems to model a particular aspect of that abstract behavior.
There's a huge amount of other stuff going on.
Yeah, there's a huge amount of stuff going on inside the brain. Like, there's a lot more complexity. So, and so once this was invented, though, it like the relationship between modern day machine learning and brains are just completely divergent. They have completely different sort of theories and foundations, and so they're no longer like trying to develop deep neural networks on the basis of the human brain or anything like that. It's just its own field, its own sort of momentum.
There was the technical stuff that sort of helped that too. The original stuff was trying to model all of these things, nodes and edges and stuff, and it was not computationally efficient at all. When we made the step to say you do all of this in matrix multiplication, that's when we started doing this is an actual.
Meanwhile, people developed, BLAS and Wayback and special silicon. But the other branches still alive and well. It's just a base.
They have their own sort of
Which was the
technology.
People modeling the brain,
Like neuroscience is
silicon
and
or
machine learning people. They're
other physical computing.
they're different people.
A huge project that got $1 billion grant to. They're doing it.
Yeah, the Human Brain Project, yeah.
Yeah.
They're building stuff.
Interesting stuff happening.
Is there like a
It's a large engine.
Oh, that's good. Yeah, so now once you've developed that model, we need to, as I mentioned, figure out what the best coefficients are to essentially almost bend or fit the model to the underlying data. From a very philosophical point of view, essentially there's an assumption that there is in fact a correlative relationship between the real life data. If your assumption is that actually it doesn't exist, then I guess you'd be doing the opposite, trying to be finding a system that proves that it can't work. But generally, like from a machine learning perspective, we don't bother with that. We just simply assume that the correlation may exist. Let's build something that does the correlation. So there's no concept of causation here at all. Everything is relied on simply the philosophical assumption that there is correlation between the variables. So how do you find a optimal set of coefficients or weights such that your function meets this sort of requirement? Well, first step is probably to just try it out randomly. You could do some sort of combinatorial random trials. You just constantly iterate potentially over different numbers of W1, different numbers of W2, and different numbers of bias, and just see which one appears to give you the best accuracy. How do you measure accuracy? You basically run every single sample over your model, and then you find out how many errors you have. Like, if your model predicts like an 8, but then the real answer is 9, you could say that the difference between this is absolute value of 1, right? And so from that, you add that all up and you get sort of like a measurement on how wrong you are on the model. And if you think about it in that way, you realize that what you might be able to do is you might be able to almost plot a sort of error surface or a loss surface. Suppose your these two axes were your like weight axes. So this is weight 0, this is weight 1. So that would be 0, that would be 1 now. And you set your bias. Let's keep your bias just to 0 for now, because I don't want to get too much into this detail why you set bias to 0 for now. But basically, on the y-axis here, we can instead call this the error. So that, as I mentioned, the error could be like literally the absolute deviations summed up of all every single piece of sample data. And imagine you were to go from here, right, and you created a grid of W0 to W1, right, and you just sort of said, okay, suppose I set the W0 and W1 to be here, what would be the error be? And the error would be maybe somewhere here. Then you do it again, and you keep doing it, and you eventually get something like a whole surface, right? And when you do that, you start to realize that there's a gradient to the surface. I'm skipping a few things to be able to get to this point. Usually you would convert your step function to a sigmoid function to get a continuous differentiable function. But
you also skip like 30 years in research.
yes, that's right.
Skip what, sorry?
I skipped 30 years in research.
But propagation.
But yeah, if you visualize this, you end up getting a smooth surface, and because it gets the smooth surface, you then also introduce a whole other sort of component called gradient descent, and then that gradient descent allows you to suppose you were to just randomly pick a point on this surface to be your initial weights, because you don't know your surface ahead of time. You have to sort of like calculate your surface by doing that, but usually that would be a big waste of time, or at least it would be a very computationally expensive if you had a much more higher dimensional problem where you had more than just 2 weights. In this case, we only have 2 weights. It's actually fairly easy to calculate an error surface. You just sort of say go from -1 to 1, -1 to 1, and then you just sort of like find the error for every single possible weight. And if you do that, you would eventually find some point that gives you a pretty optimal calculation.
At this point, we're saying we're not actually doing neural networks anymore. We're just doing simple optimization theory.
Yeah.
We've got 2 or more parameters, and we have for each parameter we have a degree of how wrong we are. So make that the vertical. You're trying to find the lowest point. So the simple thing is let's go downhill. Start somewhere and go downhill.
Yeah, exactly. So basically, you just literally pick some point, and then you start using gradient descent to find the steepest descent.
So this should be a 3-dimensional diagram.
Yes, it is.
It is.
Right. Okay, that's an example.
Force, use stuff.
And then what gradient?
3-dimensional, right? Whiteboard.
Yes.
That's a good point. We should install one for next time.
Yeah.
The TV is one of the
That would be a
3D
hologram,
TVs.
actually. Hologram.
Oh gosh.
So then, basically using gradient descent, and with another parameter called the learning rate, essentially you're now able to sort of jump to different points on this error surface. So there's a little extension to gradient descent called stochastic gradient descent, because sometimes you want to add some randomization because there may be local minima. So there might be like a point where it's sort of like it drops. And if you were just always going down, then you'd stay here. You would never come out and get to the real global maximum.
But hey Roger, how does this explanation relate to the original question? His question.
How to
What-
transfer learning rate?
Exactly.
Yes, we'll get to that. So, yeah, so anyways, with gradient descent, you can now start jumping across this error surface to get down. Alright, so that's sort of how perceptron trains. And then there's a whole bunch of other stuff that extended beyond that concept. The main thing that extended beyond it is the stacking of perceptrons. So rather than just having one perceptron, and usually the graphical notation of the perceptron is something like this, where these are the weights. Sorry, these are weights, but there's input. There are input things coming in. So these are your x's, I guess, x1, x2, x3, and then your weights are calculated against that plus a bias, and you get some output. That's one perceptron.
Sorry,
Then-
I can't resist. Like, so that, if you look at it, that's what an axon looks like. So it's got, a neuron looks like. So it's got
Yeah.
multiple inputs. They're the
Dendron?
dendrites.
I don't know the name in English.
I think in English it's dendrite. So they're the input things. They're just looking for signals. And then the single output, which is the axon, and then your bias is representing neurotransmitters. So maybe you've got glutamate floating around, which says, I'm just more likely. An excitable neuron. I'm more likely to fire. So I haven't I don't need to get to 30 before I fire. I'll fire at 5 or something.
Yeah.
But then that relates to the activation function, yeah? Somehow.
The activation function is was the weighted input above my trigger point.
Yeah.
So did it, and that's what that function is doing. It's
Yeah, exactly.
That's a slightly different parameter. That's not what we call a bias. That's more of a threshold.
yeah. So there's a threshold,
Yeah.
and then the bias is tipping, changing the threshold at which it will.
You can change the threshold outside of changing the bias, but generally speaking, you keep the threshold static. You just set it to 0 or something like that. It depends on which activation function.
It's kind of equivalent, I think it is.
Yeah.
It's
But then yeah, you can just change your bias to because changing your bias, because that gets too much into linear algebra at this point. But basically, that moves the model's origin or center around, and then that can change how it operates on the data. But as I was saying, basically, the innovation that sort of took perceptron beyond the simplistic example, because if you are aware of any sort of statistics, you'll find that this seems like a lot of complication just to do essentially what is linear regression, because you could just solve a closed form expression and do other stuff to find its weights. But what took perceptrons into what is today the big burgeoning deep learning industry is basically the addition of stacking these perceptrons. So now there's more perceptrons, and there's more of them, and then this basically becomes huge. It's like it goes wide, and then it goes really deep as well, and then there's more and more and more of them. And one of the things that is required to be able to get more and more is that you do need to. So the problem is that you need to train it, right? And so I said that one of the things that you would change to get to this point is you would change the activation function from a step function into a sigmoid function, like that. And that sigmoid function ensures that the output is differentiable. And that's important because once you stack them and you want to train them, it would be nice to have the final error, like after a giant stacked perceptron, to be able to be sort of propagated backwards through all of these neurons in order to adjust the weights in a nice, efficient, computably tractable manner.
So that, they together form a very large dimensional space. So we're trying to find downhill. We
Yes.
can't. That's the gradient. We can't calculate that if it's not differentiable.
Yeah. Now we can sort of go back to talking about what the hell is transfer learning. So these weights, right, that have been found or tuned, and imagine a big, massive network of all their own weights. The idea is basically we trained this on a particular data set. This was our data set. You know, this is the thing that we went out to the outside world and we observed. But suppose we have a whole new problem, and that whole new problem involves potentially some of the similar data set. Maybe you're still using X1, but maybe you now have a whole new kind of thing called X3. Maybe you're trying to predict something that's completely different, like Y2, right? And this...
Same dimensions, alright?
Not necessarily, yes. Generally speaking, yes, but not necessarily, because it sort of depends on what you mean by dimensionality here. Like,
Inputs to start with, and then the internal structure is the other question.
well, you see, in the context of this sort of work, in the context of work we do with images, it's always possible to simply resize them. So it's like it's not really a problem. So we could take a smaller. The dimensionality that really matters with regards to transfer learning isn't so much the dimensionality of inputs. It's if you're trying to take the weight of a smaller model and try to put it in a model that is much larger, because then you can't fill it up, right? So if the model's the same, then every weight can be copied over. But if the other model that you're trying to transfer to is much larger, then you're going to have a bunch of weights that will need to be randomly set. And if you're trying to transfer to a model that's much smaller, then you will need to drop weights basically, and you will need to decide which weights you want to drop.
And this is why it's obviously brains, right?
Yeah.
They're trying to check the weights out if you want to
Yeah.
get some transfer learning.
But they've actually done that. It works to
Sorry?
to dump a small graph into a big graph.
Yes, it can work because you can imagine that the bigger graph or the bigger model is like longer, deeper, right? So then you could potentially take a smaller model and transfer weights to the first sort of partition of the graph, and then have the rest be randomly set. So there's a lot of empirical sort of theory applied to this sort of situation of how best to transfer learn. And in the context of convolutional neural networks, where we're talking about, so you take this idea of stacking your perceptrons both deeply and widely, and now because it's so big, we can't talk about individual perceptrons anymore. We're talking about layers of stuff, layers of neural networks. And when you separate out your layers, in a convolutional neural network sense, where your inputs are images, one of the things that in a previous paper that I was presenting in this club before is that as you pass your image through these sort of layers of convolutional neural networks, and if you take the weights that are being learned in all the different parts of the network, you can actually visualize what the weights activate against, right? And what that means is that if we think of the step function or the sigmoid function, we care about the weights that produce a high number. And then the weights that produce a low number, we imagine to be something like where it just doesn't activate. So either it's activating or not activating. And when you take the weights and you visualize that, you start to see that the initial layers of a convolutional network is learning basically the fine details of an image. So imagine an image is like partitioned into smaller images. So you take any photograph and you just literally cut it up into little pieces, and these are like little fine details. And all of the sort of neurons here are learning these little fine details. Maybe it could be a curve, like a plus sign, maybe a gradient, all sorts of little sort of visual patterns. And then as you progress into the deeper into the network, and I'm also skipping a few other things that are being invented, things like max pooling and that sort of stuff. Basically, these neurons will then activate on slightly more higher order abstract systems, like faces and eyes and tires and more complex gradients, complex textures.
And the cool thing there is that replicates exactly what you see in the human visual structure, so the part of your brain.
Yeah.
Here, like the visual input goes to the back of your brain, and then we have, I think maybe at the neuron, at the retina, there's edge detectors. So is it dark on that side, light on that side? Is it like that? Is it like that? And then the next layer is kind of combinations. You have like a thing that detects a T shape and a K shape, and then kind of 10 layers in, you have a neuron that says, "Have I seen Dolly Parton?" Is it? And so on, and it gets higher and higher, and so it's.
So their perception is pretty much like stacked.
Yeah,
Results of
this architecture
patterns.
was done self-consciously. They were trying to replicate that structure in digital cameras.
Yeah.
I think was the history of it, and they did, and it turned out to be remarkably similar. We actually run it, which is super cool.
Mm.
Can you clarify, like, does that arise, like, emergently, or is it something like you need to design the layers with particular replications in order to make it do that?
No, it's actually like super composable. Like every layer is basically almost identical.
They're identical, and
Yeah.
and then you will get like, okay.
But you need certain connectivity features.
You need certain things like max pooling, which will take the highest activations of a bunch of regions and reduce it. So basically, in a way, there's a concept called the visual field of view sort of thing, and you can imagine each neuron here is operating on a much smaller partition of image.
Right.
But as they get max pooled or they get smaller into a smaller image. So this image might be like 100 by 100, but then this image might be like 50 by 50. And the next layer is now operating on 50 by 50, which means each neuron is now learning a much more composite partition. And
They're all
then,
come-
But it depends
overlapping
as it
regions.
goes farther, yeah?
yeah, so that's the other thing. Each output also gets deeper. So yes, it's 50 by 50. So in color images, we talk about RGB. So there's a depth of 3. There's like a volume that's actually being processed. When you apply your convolutional layer into it, what you get back is another volume that is dimensionally height width smaller, but its depth is actually deeper. The reason why you have that is it's almost as if you're sort of saying that there were 3 layers of information here, and now I have converted it into a smaller image that has much more layers of different kinds of things that I care about. So maybe one layer might be a particular gradient that I've sort of activated against another layer, like something else, and so on and so forth. And then eventually it gets much smaller until at the very end it's literally a single vector, where it's what they call a 1 by 1 vector. So it's like 1 by 1, but then each depth is the actual classification label that you care about. So if you're classifying between 0 to 9, then this would be 0, this would be 1, this would be 2, this would be 3. And remember, everything that's inside these volumes are just numbers. So this is a volume of numbers, there's another volume of numbers, and this is also a volume of numbers. But because it's a 1 by 1 volume, you just think of it as a vector. So it's a vector of numbers. And ultimately these numbers indicate whether this image activated all of these parameters and biases such that you get back a vector of numbers where usually the highest number is the highest activation. So that means you sort of like said, I think this image looks like a 1. I think this image looks like a 2. So on and so forth. You get all, and if you get like a similar number between say 3 and 4, actually one of the things that do look similar, I believe, was 6 and 9. So you get 6 and 9, right? So you'll often find that the numbers for 6 and numbers for 9, sorry, not 6 and 9, because of rotation invariance, it's actually 4 and 9. So you know that 4 and 9 actually sort of do look similar, especially if people sort of like do that, right?
You can only tell which is which by looking at that person. All the digits were written by that person.
Yeah, exactly. So in that particular scenario, you'll find that this thing does produce similar activation numbers for 4 and 9, and it will be like, yeah, of course 4 and 9 look similar. That's to be expected.
Roger, how do you interpret visually the fact that the network gets deeper as you go along? I mean, it's like a composition of learned filters so that you build more complicated patterns to it.
Yeah, so
That in the end you really have the thing represented in all of its characteristics.
yeah.
Each class.
That's right. So, the depth of the network sort of represents all the different things you've learned about that image. And so, as you go deeper, the actual sort of like image gets smaller because you've sort of collapsed that visual information into a set of kind of categories, things you might have learned about it, and then. Yeah,
And
that's
hopefully acquiring meanings, which in the original Pixel didn't have much information in it. It was just, okay,
Yeah,
it's a
exactly.
light blue, it's a dark gray.
Yeah,
The-
exactly.
The later Pixels are like, no,
But
this
as
is
regulations are
definitely
being
Abraham
traced
Lincoln.
around
This
each
is the dog,
pixel.
this
Yeah.
is Dolly Parton. This
Yeah.
is,
So you've gone from like one.
It's kind of the understanding is unraveling, yeah,
yeah.
along the.
Then you've reduced this image into a smaller image, but then it's deeper.
Understand. I don't know if understanding is the correct word, but you
And,
know, the assigning of
It's not a-
meaning
Yeah.
is unraveling
It
as
should
it
be
goes.
understanding if we're doing machine learning.
Yeah.
So getting back to transfer learning,
Yeah.
that's like taking weights of like one model and putting it in the context,
Putting it in another model.
or in another model.
Yeah.
Without having to do much retraining, I guess.
Hopefully you don't need to do as much retraining, because one of the problems convolutional networks is that the number of parameters is significantly very large. It's just it gets the deeper you go, the more parameters you have. The wider you go, the more parameters you have. So now you're dealing with like things like 90 million parameters that you have to optimize against, and obviously another reason why deep learning has become so important is because the computation capability has sort of caught up to the theory, and so now we have a lot of very powerful GPUs that can do a lot of these matrix calculations in parallel and update all these numbers in parallel.
So you build lots of cool models. We have to do a burn a rainforest all the time.
Yeah, like we did today. We just got a server with 4 RTX 2070s in it.
Oh, bathroom. Yeah, this is interesting. You can let yourself out, but you're gonna have to. Either I come you to the bathroom, which I prefer not to, or if you ring the bell when you come back.
Yeah, so basically, transfer learning, you take the weights of an existing model, you move it into a new model,
With the hope that it will work.
with the hope that.
Do you take all of the weights or some of them?
No, you don't need to. That's the key point, right? You know how I said that in your convolutional neural network, earlier layers will learn like more finer details of
Yeah.
the images. It turns out that if you're in a similar problem domain, you can simply assume that the finer details of the images are similar in other problem domains as well.
Right.
That way you can take all the weights from your first layers and then just sort of copy it over to your new network. But you imagine that here, in this case, I'm just trying to classify numbers, right? So in the beginning, I might be working against essentially little curves and other little details of how you might draw a number. But later details become much more specific to the idea of a number itself, the exact actual shape of a number. If I was then trying to transfer these weights into a situation where I'm trying to classify between dogs and cats, the later weights will not be as useful, because the later weights we're learning what a number looks like, but the later weights of the new model has to learn like things like a snout, the look of a snout, what an ear looks like, what an eye looks like, and these look quite different from them.
So that's why we kind of basically exclude the top
Yes.
when we're transfer
So
learning.
Yeah, so when you could say, okay, I'm not going to transfer this, but I'm going to transfer this and this, and you move it into the new model, and the new model's sort of third layer or however many layers, they're just randomly set. They're just left as unknown for now, and then you perform the training on your new system as well, but you can do it in less sort of iterations than if you were to start from scratch, because these things have already become optimal. And then there's a bunch of other problems that get involved at this point once you start getting into things like overtrained things where overfits and regularization, that sort of stuff. But that's supposed to answer the question, I guess.
Understood what transfer learning is.
Yeah, I've understood transfer learning now.
As a designer of one of these neural nets, do you have to develop your own intuition about like how many layers you need to?
Yes. I mean, no, but yes.
Do these days, because we still don't quite understand what we're doing.
Right.
There's a
Maybe
sort of,
eventually figure it out.
it's sort of like you can take pre-existing models that have been developed, usually in an academic situation, and apply it to your problem and see if it sort of works well. And then if it doesn't work well, then you need to start developing an intuition as to what you could potentially do to make it work better. And in a lot of cases, it's not really about the model so much as it is about how clean the data is. Yeah. So when the data is not clean, the model's not going to give you good results no matter what. So the first step is usually getting cleaner data. And this is exactly why.
Exactly.
Yeah.
Places I work that were doing machine learning, the bulk of people were actually working on the data cleaning then. So
Exactly, the translates biased usually, and
Auto exposure.
people don't want to admit that they are experiments.
Yeah. So our food was very close. The driver's now just across the harbour bridge heading north. And still going north, so I don't know what's happening there.
That's bad.
Is there a way to talk to him?
Does that mean he's gonna pay a toll to come back and
I guess so, yeah.
Oh, that's
Just
terrible.
like park somewhere there and come back home. It's just much
It's probably,
faster.
it's probably on a scooter. Do you pay tolls for
On the
your
I saw him coming out the car expresso, I'm like,
I
are you
think if you
gonna...
went the wrong way,
He
it's
took the-
probably not on a scooter, because on a scooter you could. More easily turn. Oh, you mean like a road scooter?
He's moving too
Yeah.
fast for a...
Not a bike.
sure?
I think it's a...
Not a bike.
I don't know.
Most
Toyota Corolla.
Uh,
Haha.
So he's in North Sydney now.
No, that's no good.
Maybe he just has lots of to-dos.
Yeah, it could be a multi-stop.
That's true. Anyway.
Alright, so going back to this problem of one class transfer learning, as we saw an example there with basically you get numbers, and as I mentioned with like it's model parameters are all great and stuff, but one of the big problems is that the data itself is unclean. It becomes very difficult to work against anyway. And one aspect of uncleanness of data is the imbalance of data. So if like data is too much on one class and too little on another class, your network will often be biased towards one class or another. Think about this for a moment. If like in your training set, 90% of your data was of one class and 10% was the other, you can get 90% accuracy just by always flipping a coin and biasing it to 90%, saying that it's probably that class.
So I'm reading this as like some of the things you see in the headlines. So, should this person get a loan? Oh, are they from wealthy white person suburb, or are they from, some other
Yeah.
suburb? And you find, we just trained a, racist,
Yeah.
bigoted.
Yeah. I've always thought of that was funny because that's mission accomplished in a way, because they're trying to replicate their existing model, and their existing model is working out. So you can see that neural networks are lazy. They will literally go there for the easiest way to achieve your metric, right? So if your metric is simply accuracy, and then you give it unbalanced data, it will just be like, hey, I don't need to learn about this data. I can just say 90% of the time it's this class, and then it's done. So
There's a famous example of identifying tanks.
yeah.
And the thing that they identified was the sky was blue.
Yeah, that's right. So when they gave them a picture of where the tank's not in the thing, and it wasn't able to realize it. Yeah. So that's actually one of the reasons why visualizing the neural network is very important, because you're sort of trying to sanity check if it's actually learning the right things. However, for this particular paper, the main sort of innovation here is dealing with situations where you cannot solve the imbalanced aspect of the data just by sort of balancing it or oversampling the underrepresented or undersampling the overrepresented. Because fundamentally your problem is dealing with an anomaly sort of situation where there's always going to be less of that anomaly versus everything else. So this model architecture is pretty interesting. So let's skip to the second page. And in the second page is a diagram here, which basically shows transfer learning to some extent. And what the architecture in which they're proposing is on the far right. And basically, it's as if you took an image from an existing data set that has nothing to do with your problem. So for example, you take CFAR10 or you take ImageNet.
Do you need help, Mark?
Is this related to the black hole? Imaging the black hole? Because they were talking about something like trying to find an algorithm to visualize the black hole, but they trained their system on like everyday images, and I don't know, it was like somehow.
Yeah.
Oh, yeah.
Well, I'm not sure about that, but in this particular case, we're going to make use of two data sets
Right.
to solve this problem. One data set is the data set of the thing that you want to detect, so the anomaly itself. That's your unary class. So, for example, let's say it's a dog. all dogs. You want to always identify dogs beyond anything else. So you're going to have a data set of dogs. Then you're going to have also a data set that is just arbitrary of lots of other things. In fact, the more arbitrary, the better. The more variability in that data set, the better. So let's say you take the data set of all of ImageNet, which is 1 million images of 1,000 different categories, and you take that. And then you sort of train them together, use both data sets. This architecture also introduces two new loss functions, one called a compactness loss and another one called a descriptiveness loss. These are composed into one single loss function. You also translearn by taking weights from an existing architecture that's been trained with really anything, because what you're really trying to do is you're trying to minimize your training time. It's not really fundamentally revolutionary. Oh, well, I don't know, some people might argue transfer learning is revolutionary because there's a cool little thing you can do once you can introduce transfer learning. You start imagining a world where you could potentially stack pre-trained models continuously, but I don't know if that's going to happen soon. So what they start talking about here in the bottom paragraph of this page.
Where is it?
Yeah, just go down to the bottom of the page. So in this work, we focus on the task presented in case C, where the training data from a single class is available. Strategy used in case C above uses deep features extracted from the pre-trained model, where training is carried out on a different data set to perform one class classification. However, there's no guarantee that the features extracted in this fashion will be as effective in the new one class classification task. In this work, we present a feature fine-tuning framework which produces deep features that are specialized to the task at hand. Once the features are extracted, they can be used to perform classification using the strategy discussed in C. In our formulation shown in figure 2E, which is the diagram on the far right, starting from a pre-trained deep model, we freeze the initial features, they call it GS, and learn GL and HC. So you remember how we said that things like we usually call the function that we can train the H function, which is the hypothesis function. In this particular case, they've just chosen H and G because there is in fact a layer of a network which contains the final weights that convert a convolutional volume down into a vector of sorts, and that is usually that's like a pure neuron. It's a pure bunch of neurons, which means that it doesn't have any bells or whistles. It's just a normal neuron that takes all the inputs and then produces an output. Whereas a convolutional neuron is usually a bit more sophisticated because it has to take sort of like a sweeping window of inputs of the volume that's been given, and then there's also max pooling and that sort of stuff. So they've just decided to call the part which is what we call the fully connected network HC, whereas the parts that are convolutional are just notated as G. Based on the output of classification subnetwork H of C, two losses, compactness loss and descriptive loss, are evaluated. These two losses introduced in subsequent sections will be used to assess the quality of the learned deep feature. We use the provided one-class dataset to calculate the compactness loss. An external multi-class reference dataset is used to evaluate the descriptiveness loss. As shown in figure 3, the weights of G, L, H, C are learned in the proposed method through backpropagation from the composite loss. Once training is converged, the system is, so anyway. In summary, this paper makes the following 3 contributions. 1, they propose a new engineering scheme called Deep One Class Classification, which is targeting one-class problems to the best of the knowledge. This is one of the first works to address the problem. This paper was released in 2018, 2019. We introduced a joint optimization framework based on 2 loss functions, compactness loss and descriptiveness loss. And we'll get into that more deeply. And then let's proceed to the next stage. So there's section 2, which talks about some of the people who've sort of worked on this sort of problem in a similar fashion, but they don't use this sort of, this kind of method to do it. I don't find it particularly that interesting. Let's get to the.
Yeah, it's not interesting.
Let's get to the
Let's
future.
just keep it. Yeah,
So the
section
food's here,
3.
so whenever you want, we'll have a short break and go get food from the kitchen and bring
That
it
would
back.
be perhaps a good moment, yeah, because then we're just gonna start to creep in, I think, because
Yep.
it starts now, actually.
Yes.
So let's see.
Okay. So you see bits of category theory kind of coming into the edges of functional programming, like, so where does our lens representation come from? Scroll left functor, like A to S to F, T goes to A to where does that come from? It's the unique line. And so, yeah, see people talking about pro-functors and things. So none of these things are really all that hard, they just kind of come from genetic category theory. So if you can use them without knowing category theory, so the answer do I need to learn it? The answer is no. But if you're one of those people who wants to open up the box and see how everything works, you want to write a new lens representation or something like that. Then it's handy.
So from what you say, it's not that useful as the people who live together.
I mean, I really like it. I think I've been learning it for 22 years. And still learning things I still find fascinating. But it does get overhyped a bit. So yeah, I wouldn't be sitting there thinking, oh, I'm not a functional programmer if I don't know category theory. The parts that you get most used of are just the idea of composing things, and that's a pretty basic thing.
I expected from it to be a study about composition, how to compose programs in this kind.
Yeah, well, category theory is the study of compositionality.
Let's continue.
Yeah, we're
Distracted from that.
Yeah. So on the
Section 3, yeah?
yeah, section 3. If you go scroll down. So it says that in this section we formulate the objective of one-class feature learning as an optimization problem. In the classical multiple class classification, features are learned with the objective of maximizing inter-class distances between classes and minimizing intra-class variances within classes. What that means is that we want features that activate on the difference between one class to another class. While at the same time, for the different, say, images within a given class, you want them to sort of like ignore the minor details, the noise. So like, if you care about dogs and you want to classify dogs against cats, you want features that determine the difference between a dog and a cat, and they're the ones that activate. So whether they activate or not tells you whether it's a dog or a cat. You don't want features that activate on the differences between different kinds of dogs. So if all dogs have, I don't know, like a particular shape of ears, you don't want features that activate on that shape of ears. You want the features that activate on the difference between, say, the dog's ears and the cat's ears. In the absence of multiple classes, such a discriminative approach is not possible. And in this light, we outline two important characteristics of features intended for one class classification. So he says compactness, which is C. A desired quality of the feature is to have a similar feature representation for different images of the same class. Hence, the collection of features extracted from a set of images of a given class will be compactly placed in the feature space. This quality is desired even in features used for multi-class classification. In such a case, compactness is quantified using intra-class distance. A compact representation would have a lower intra-class distance.
This seems like a similar property to
Yeah.
Occam's razor, or things minimizing energy or something. You want the simplest possible description
Yeah,
to be
so-
clustered in phase space.
Yeah.
Features.
In terms of intra-class distance, it would be as if you took all the images of a given class and you calculated some sort of metric that tells you how different an image is from another image. Now, if your sort of like function is well tuned for understanding a particular class, you should show a low distance between images of the same class, which is just basically similar to what we just said previously with regards to having features that activate on the difference, not the difference between classes, not the differences within classes. And descriptiveness, D, a given feature should produce distinct representations for images of different classes. Ideally, each class will have a distinct feature representation from each other. Descriptiveness in this feature is also a desired quality in multi-class classification. There, a descriptive feature would be a large interclass distance. So at this point, it's just basically describing these are the two objectives for multi-class classification. And it just turns out we have the same objective in unary class classification, but we have to sort of do it slightly differently in order to meet these objectives. It should be noted that a useful discriminative feature, both of these characteristics should be satisfied collectively. Unless mutually satisfied, neither of the above criteria would result in a useful feature. With this requirement in hand, we aim to find a feature representation G that maximizes both compactness and descriptiveness. Formally, this can be stated as an optimization problem as follows. It has G hat equals the maximization with respect to G, capital D, descriptiveness applied to G on T, where G is this is your model, is your convolutional neural network, and plus lambda on C on G of T.
I
And
guess
T,
it's supposed to be brackets around the whole thing.
yeah, yes, maximization on top.
Everything.
So lambda is a factor that adjusts how important compactness is relative to descriptiveness. So if lambda is 1, then both are equally as important. But if you tune your lambda smaller, then your compactness is less important.
So D is like the separation property.
So it's D is how much distance there is between different classes, and C is how much you sort of understand that features of the same class should have low distance. You need low intra-class distance, high inter-class distance.
Are they just making the cost function more complicated? Like in normal neural networks, would you just have a single maximization, a single function?
Well, it's interesting because one must then talk about exactly what is the cost function used in normal multi-class classification. If we look back at the problem of binary classification, and I said about how at some point you would then calculate all the errors, and there's a number of different ways you can do this. You can do things like least absolute deviations, where you find the distance between your predicted and the truth. You add them all up, you get the absolute value as well, and so you have this number that represents how much distance was away from your predictor and your target data set, the truth versus prediction, and you want to minimize that. But then you can also, that's called that's called LAD, but I don't think it's, I forgot which one's L1 or L2. Oh, sorry, that's the L1 loss function, yes. Let's call it, that's often noted as L1. Then there's a one called L2 loss function, which is then, you do the same thing, but instead of getting the absolute value of the distance, you square the distance. So in that case, your distance becomes positive because you squared it, but it punishes more outliers, while also things that are very close to each other, it minimizes it. And then there's L2 mean, which is then you do the same thing as L2, but you divide by the number of samples there are. So you get an average error.
Those are all single input functions. I want to handle it, what I mean by single there.
Well, you can do things like you take a
single measurement.
Yeah, all of it's a single measurement at that point. It just comes down to one number that you're trying to reduce. Yeah.
So is this technically, but there are two sub-pieces that are distinct?
Yeah, exactly. So they're sort of trying to, well, that's binary classification first. But then when you go into multi-class classification, the actual cost function is a bit different. It uses a thing called softmax, and that's gonna take a little while to.
So you've got like 3 different things you just talked about.
Yeah.
So that thing is saying, just for anyone who doesn't know, it's like, how does the error change once you get closer and closer to your target? So the first one is the basic thing, it's just downhill, downhill, downhill until you get there.
Yeah.
And that has, and the other one is, well, as you get closer, you're less wrong, less wrong, less wrong. We attenuate that, and there's other variations that affects
Yeah.
different things, and
Yeah. So, so binary classification is an easy example to understand because
You can draw the diagram.
yeah, you can draw diagrams really easily. Once you get into multi-class classification, there's this other concept called categorical cross-entropy, and at the end of the day, it's sort of just trying to generalize it to multiple different classes, but you're also sort of just quantifying how wrong you are as well. But I don't actually know how to explain categorical cross-entropy. Like I read how it works, and I just sort of accepted it. But there's a lot of depth to it. Like
Sort of,
distance between 2 distributions.
yeah, there's distributions, there's KL divergence, there's things like information theory.
so even in a multi-class thing, right, you'd say my input was this particular type I expect, and my output was whatever the hell it told me.
Yes.
That's sort of just comparing, you have one comparison, even though you're doing it across all of your inputs, right?
Well, you're doing it across every single sample you have. So if you
Yep.
have 100 samples, you ran your model on each sample, and you get a prediction for every single sample. You can compare your vector of predictions against the vector of ground truths, and you're just doing a like a minus element-wise, and then you get your deviation. Then you can get the absolute value, or you can square it, and then afterwards you can sum it, and then you can divide it by the total number to get the mean if you want. And you just want to reduce this number.
But it's like, it's a single function, right? Like,
Yes.
And
Yeah.
this is trying to do 2 functions at once. This is saying, do
Right,
do
yeah.
that, but do it across compactness and do it across descriptiveness.
That's
and
true.
For some reason,
Yeah.
that is better.
Yes, I think what they're describing here is a different formulation of an appropriate loss function for optimizing multi-class classification. Because, as I
So
mentioned,
this isn't actually.
Yeah.
Okay.
so the actual cost functions used for multi-class classification is basically the categorical cross-entropy. That's the word that's actually used. But again, like there's a difference between abstraction and implementation. Like he's trying to say that forget about the implementation. Just think about this from an intuitive sense of what the purpose of this thing is. It's trying to learn the difference between classes while also ignoring the differences within a class. He's just sort of modeling it from the like
Actually, you can do
Yeah.
proper theory on that one.
exactly yeah.
So, when you're talking about that, this D and C, just maybe remember from one of Douglas Hofstadter's books. He's not talking about machine learning,
Yeah.
but it kind of fits. He's saying, how do you define the letter A? And then he says it's basically impossible. He has like I was trying to find it, but I can't find it. So gets a whole lot of 20, 30 different fonts and draws letter A. So maybe it's that, maybe it's that, maybe it's that, maybe it's a weird font when you do that, and then there's all these like weird fonts where it's built out of bricks or something and it's 3D, but we can recognize it, but it actually is not any of these. And so it turns out there's no way you can define the A-ness. It's just like a set of patterns that we've learned. So I think that would be a good example of a feature which is not what you're looking for here. It's really hard to, given the set of graphics, to give I don't know, maybe I'm simplifying or it's not.
Wasn't there with this guy?
Yeah, they're kind of scattered in between, like separating them from the other letters is hard.
Yeah.
And it's just, we have a very complicated model in our head of what is an A.
Yeah.
It turns out, you think it was simple, but it's actually really hard. And,
Yeah.
I can't remember all the other examples.
It was a highly amorphous.
Wasn't there with this guy that you said?
Douglas Hofstadter.
Big Bang Theory?
Sorry?
From the Big Bang Theory?
Oh, I don't know. I've never seen that. But he wrote Good Leisure Park, Men of Magical Tamers, and all of other books. And he's a guy who came up with Hofstede's Law. It always takes longer than you think, even when you take into account Hofstede's Law. Relevant to
A more popular side?
he's a kind of philosopher, quite interested in computer science.
Charlatan.
No, he's not. He's not a child.
I actually did I studied this concept a little before, but more from a psychology perspective. They used to talk about this concept of Gestalt. There's the Gestalt of an A that you're not reducing it just to its fundamental parts.
Yeah. What is it what is the definition of A as this one?
Yeah,
No.
there's a Gestalt representation. So as I was kind of saying, that this formulation is not the actual loss function that we actually use when we train the multi-class classifier. It's just a theoretical model, an abstraction of that.
You're still on one, yeah? Just to be clear here.
Yeah.
You're still discussing
So,
one.
yeah.
So, but intuitively that could make sense, yeah?
Sorry?
You're trying to maximize whatever quality that makes the same class the same and different classes the most different apart.
Yeah.
This would mean that this is classifying something else. There are other visualizations for this, which I would prefer, which is a radial plot. It'll be much more precise if you think of classes. So I'm classifying 1 against 1. If you don't put Roger didn't like this plot, but I would prefer to have in our system, yeah, but Roger wanted this curve right here, which is very good to read, I think. It's easier to read on a polar plot, so you have the axis that goes here. You have 10 in our case, yeah?
So
one,
one
two,
for
three,
each
yeah. For each class. Let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, something like this. Yeah? We would expect, for example, that the classifier of 4 would be something, it would have some classification on the 9. Yeah? So you would have something, a chart like this, similar to this here. Because it would happen also that 4 would classify 3, or the classifier for 5 would classify, so you would expect this. The perfect measure would be just a dot. So that 0 classifies only 0, not 1, not 2.
Or a spike.
So yeah, so when you have the confusion matrix and you go across the points, you would go doing this actually. This is one round when you go around the confusion matrix. So yeah, this is what you would expect. Something more like loads of. So if you compare all the possible classifications, which would be same thing as these raw curves for all the classes, we would have 10 curves here.
Right, yeah.
And the closer they are to the center, the better your model is.
The center, or you want them
The center.
strongly on one axis?
The center.
Oh, it's the number of
Yeah.
misclassifications.
Exactly.
Right.
The number of misclassifications is represented in each axis.
Right.
So yeah, that is the. So each curve is one classification for in respect to 0, for example. 0 has 10 hits of 0 itself, 9 of 1, 3 of 2. I don't even understand. Yeah, 2. So this is what it represents really. The number of hits of the misclassifications in each axis, yeah? So you get the classifier for 0. You should be classifying only 0. But then you see some hits of on 1, axis 1, so 2 hits, 3 hits, 4 hits, so then this would make this
Yeah, so from what you're saying, it wouldn't be focused, based on what you just said, it wouldn't be focused on the origin. if 0 only classifies 0, then you'd have all the hits on 0. So it should be.
The arms are negative, not positive.
Yeah. So
His drawing is confusing to start with. Like that line between 0 and 1 shouldn't exist, because 0, if we're looking at 0, there shouldn't be 5 negative hits on 0, because it's the 0.
Oh it's, no, yeah, oh yeah, true, yeah. Because you're comparing what you're classifying against all the others. So it will be 0 here always.
Right.
So it will be something like parting from here. Yeah, that was confusing. Sorry.
Because that logically.
Yeah. Otherwise, we have to have 2 zeros here.
If they weren't showing a diagram, you
Yeah.
wouldn't appear on your
Yeah.
axis.
Yeah. So you're looking at these and comparing against all the others, and then you're looking at the classifier 1, looking at all the others. So that's. I mean, the plot's really pretty. It's called cowboy plot. So it looks really, really, really nice. But yeah, Roger just didn't like it.
I've got to be careful with diagrams and how much they lie. There's some work on it, like.
No, yeah, but they tell something. It's much better than the curves, yeah. And if you calculate the area, it's the same.
You've got to be careful.
Well, the AUC calculation of this is very complicated though, because it's like a volume.
No, you really just go across the matrix, summing the dots, yeah.
It was a volume calculation for this.
Anyway, we should let.
Oh yeah, there was, yeah. But it's implemented already, yeah, in Python even.
So
Is it?
Well,
So it's
we started from testing procedure, how accurate it was. But my point was, if I'm reading that horrible diagram correctly, they're starting off at roughly we're covering most of the space, and they're getting to we're also still covering most of the space. But it's a bit better.
from 80 to low 90s, so we're doing. It's gone from good to pretty good.
But I don't know what the AUC is of this case. Is it the AUC of the single class, or is it the AUC of something else? Entirely different. I don't know. No, it's explained over there. But if you look at total loss, you can see there's a significant drop that you can drop your loss significantly just within 2 epochs. This sort of makes sense. Because it doesn't take very long to train this. That's the main idea about this. Is just simply because a single class data set is usually probably not that big.
So it's interesting that descriptiveness loss does what you expect, kind of decreases, but compactness kind of grows and then shrinks again, depending on where exactly that green line goes, which is unclear.
Is that because
I'm guessing it's somewhere under the panel.
And so you
because of
hold
that shows an lambda? Is it lambda that shows the bias description?
It sounds like in order for the model to get more descriptive, it has no choice to be a bit less compact, but then somehow it gets itself into a
It
configuration.
reminds me of GAN to some extent, yeah. It's kind of always this dual behavior, kind of competing one against each other to.
Yeah.
Yeah, and then there's this
I
thing.
wonder if you can. It's kind of remodel it as again. So it's something. It is something similar, right?
Yeah, actually,
But they are exactly the same. Again, it's two separate
Exactly,
networks. This
yeah,
is the
there's
same network.
It's
with
a
two
two-player
loss
game,
functions.
as
That's what the multi-objective optimization occurs. Is where you're sort of like getting typed in both directions.
This is a single network with two personalities.
Yeah, but it's kind of frightening. Yeah, I mean, you're expecting this asymptotic behavior, but then it could be that it just like explodes, and then you're just like you have no idea what's going on. You know? So then you have a U there, not like something more like.
Can I draw like a stupid analogy? But maybe you've asked someone to do something, and you've also told them be neat, and they're rushing around and they're doing everything, and temporarily their desk becomes very, very messy, but finally they work out what they're doing, and then they tidy the desk again. Maybe it's something roughly similar. You like your you're getting
it reminds
temporarily you have to get a
Objective.
non-compact thing, but then finally you get.
Mm.
If there is an answer to be found, you eventually get down to it.
Yeah. So once you finish your training, you can then proceed to do testing, and they say that it involves 2 phases: one, the template generation, then the matching. For both phases, a secondary network of weights learned during training was used, shown in figure 5b. During both phases, this excitation map of the feature extraction subnetwork is used as the feature. For example, layer 7 FC7 can be considered an LXNet-based network. First, during the template generation phase, a small set of samples are drawn from the target training data set. So this is kind of interesting because if we look at the left side of the chart, we have the reference data batch at the in the reference network, but then later it's just the samples of target data. If you scroll up. So the top data set is not a batch of the reference data anymore, it's actually a batch of the target data.
All right, so something from here we get some samples.
Yeah. And the samples create the templates. And these extracted features, these templates, are then stored and we use in the matching phase.
So the template is just a name for what comes out of the G
Yes.
network.
Yes, given the target. That's a batch of target data. I'm not entirely sure if that happens on every single test image that is sent in. That seems unnecessary. So that would seem like a two-phase thing where you do this ahead of time and then you have that.
Weird to me that you have to send it in. It hasn't actually learnt that. In a sense, what is a weird chair? I'll remind you what a normal chair looks like, and then I'll tell you.
Probably this is how you set out for the first run. The diagram isn't trying to capture how you run it each time.
Yeah.
So when you're setting it up the very first time, before when you finished training, you have to get the outputs. You don't really need the single input, but you have to get the output so you can feed that into the classifier, and then you go, oh, let's just test the first image. And then, and then you've got the whole classifier data and you get the first.
Because the classifier essentially in this problem domain is about saying whether this anomaly is part of the class of the class of anomaly that you care about. So you have to sort of essentially run it through your network, which has just been trained, but with these two objectives. And then you'll classify in that those templates are stored in the classifier. And then later, when you pass the test image through the same network, you're getting that feature map, and you're comparing that feature map against the other templates, and it says on the next page that comparison is KNN, and just
Or
basically
SVM.
or SVM or anything like that.
Right. So it is what I think. It's like people with relative pitch versus absolute. So you say, what is that note? And they say, I don't know. Tell me what middle C is. Say, okay, it's a high E. And people with absolute pitch say, why do you have to say that? That's ridiculous. It's like saying, what color is this? Like, well, tell me what red is first, and then I'll tell you.
And your example here is
There is this kind of connotation of bargaining in this thing.
So we find it completely natural for pitch, but we find it really weird for color. You just know what red is. No one has to show you blue first to remind you what the starting point is. But yeah, this seems more like the pitch thing where it has to be.
When you're like looking at an image in the dark or whatever, then you
Maybe really close differences. You're doing some deep analysis of something. You've got two different shades of blue.
Well, yeah,
if
they're very
the dress is
close.
blue or gold.
If you get if you get different, if I show you a blue, then I show you another blue, and I show you another blue, you all keep thinking it's blue, but like you have to see the difference to be able to quantify how blue something is.
You also need the language for it. That's a different thing entirely.
Yeah. Okay, so now we've got the templates, and then you have the matching function is the score function, and F is applied to Y, which is the test image, bar GT1, GT2, until GTN. So that's why I'm saying the bar is almost like it's like an extra comma, really, like a super comma, because they're all parameters to your F.
Right, yeah. So people do this in other fields.
And F dot is the matching function. This matching function can be a simple rule such as the cosine distance, or it could be the more complicated functions such as blah blah blah. And then there's Euclidean distance. After evaluating the match score, y can be classified as follows.
Where you apply the threshold.
So I wasn't sure about the previous sentence. It said that in this work we choose the simple k and n described below, but they describe k and n by simply using Euclidean distance at the end of the day. And then finally, you've got a step function at the end, which is just if s of y is less or equal to threshold 1, if it is greater than threshold 0. So you get the step function at the very end. Anyway. And that is it for this architecture. Oh, you know, like when I was talking about, I don't exactly know how the backpropagation sort of works. It seems like this extra paragraph does actually mention it a little bit. So it says, in the alternative implementation, only a single core network with functions g and hc are used. 2 loss functions branch out from the core network. However, in this setup, the script in this loss is scaled by 1 minus lambda. First lambda made equal to 0, and the data batch from the reference dataset is fed into the network. Corresponding loss is calculated, and resulting gradients are calculated using backpropagation. Then lambda is made to 1, the data batch from the target dataset is fed into the network. Gradients are recorded same as before after backpropagation. Finally, the average gradient is calculated using 2 recorded gradient values, and the network parameters are updated accordingly. In principle, despite of having a lower memory requirement, learning behavior and alternative implementation would be identical to the original formulation. So yes, you can alternate the training, or you can do it in parallel.
It's weird that they say you need to double the memory.
Double the what?
So at the start you've got to double the memory, even though, because the weights are the same, it sounds like you need.
Because you have to store the first round result, the first round of gradient. You can't throw it away. You don't update. You don't actually update. It's that they're getting on about later on. I do backpropagation. The resulting gradients are calculated using backpropagation, then lambda is set to something else, and the batch of the target data set, the gradients are recorded the same as before. Finally, the average gradients, you need the original gradients, you need the new ones, so you can do the average. You might be able to play some tricks to like do a rolling average of some kind, but probably not.
Right. I'm thinking it's the same data, so why do you need to throw it twice? But they're
2 different data sets.
well, it's going into.
You need to
it's going into a GPU, and a GPU can't do doesn't have fancy tricks of this is a shared variable. It's
You have to do the forward pass. You have to remember the feature match.
you need to keep it for twice as long, or have it stored twice, which is what you're saying.
Storing it twice thing is what I'm saying.
Yeah. Or you do one after the other, so you've got that memory for twice as long.
That's it. Yeah. They have an implementation of this on GitHub. So you can only see the code.
Yeah, I'll give a box of chocolate for the one who gets the thing running.
Yeah. It's written in PyTorch using Lua.
No, cafe.
Cafe?
Yeah. Seriously, I'll buy a chocolate. Swiss chocolate. Late.
But the paper also has some magic numbers in it, so both of them could be.
I mean, yeah, there's, yeah.
Both of them could be smoke screens.
Yeah. And I realized that they've really taken chunks of code out of the repo. You can realize if you go and Git, you see they took everything that's useful out of there. So you see just the skeleton of the project. But yeah.
If you go and Git, if you're saying you can see that they took it away and Git, then you should be able to see the original.
No, no.
Did they delete the references?
I think they were using SVG or something like this, you know, and then they just really patched what they wanted to be visible to others.
And we have some sample images. Quite weird looking at them without knowing what you're supposed to be looking for.
Yeah, I didn't understand these. I think it was the
Top
same,
3 rows
the
are
same
normal.
person, yeah.
Top 3 rows are normal,
No,
bottom
it's
3 are abnormal. So plain, 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 weird, plain, very weird, plain. Chair, 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 weird chair, weird chair, weird chair.
Yeah,
That
so
looks like a drum.
This is novelty detection.
Boat, 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 weird boat, weird boat, weird boat. Basketball hoop, basketball hoop. Why is that one weird? Because of weird angle?
Yeah.
Because it looks.
It's from from the from down.
Yeah. Otherwise, it looks normal. Like that looks normal, but maybe the
Fishing net. Fishing.
could be confused with something.
The first one.
Oh, is this is what it came out as abnormal? Is that
Yeah, it's saying
this is the results?
no, it's actually a different data set called the abnormal 1001.
Oh, so used for evaluation. Yeah, sorry. I see
So
now.
there's actually a data set called abnormal 1001.
The face one is weird. Why are some faces normal and others? I'm sorry, you have a weird face, and the computer confirms it.
Very politically incorrect, yeah.
This whole thing of like, you can excuse your biases, like well, the computer said it. Sorry, not me. It's just you can't write. You got a
Yeah, you have
good
an
face.
abnormal face, you know.
Like from
Like
literally.
offensive.
Please promote you so you're fit for work. Have a green card and have a normal face.
It's algorithmically determined because it's Euclidean distance, right? Your face's variance is actually out of the mean.
Just like some plastic surgery.
It's even more
You make it big.
Even the faces variance is out of the mean.
That seems very. That's weird. So one cartoon backpack is okay, and another cartoon backpack which doesn't have eyes is apparently weird.
Oh, man. But this is just an evaluation. This is not actually what the system predicted. Like,
So it's not it's the humans who are wrong.
yeah.
Well, that makes it. That's even weirder. What's going on with these, and what the hell is going on with the photos? Like these are all guys with glasses. There's nothing to distinguish.
It's the same guy. It's three different faces.
Yeah.
vertical.
Yeah, that's what I.
They've done the first set.
Oh, in B and C, columns are formed by images from a single class.
Yeah, it's the same person.
Okay, right. That's why we're getting confused. There's nothing.
There's actually nothing wrong.
They're all just different. That was very complicated.
BNC.
Three
Right.
people across some bad days. Yeah. So
Monday, Friday, Monday, Tuesday.
exactly. The last one on the right, bottom right is like Friday. First one.
First one
Monday.
is smiling. Yeah, the only smile.
Yeah.
Someone needs a better word.
Exactly, something like this. And then the one next week, working on Saturday, something like this. I don't know.
To be honest, the only mystery I have about this is how that does the actual weight updates
Yeah.
and ties it up together.
Especially if it doesn't in parallel.
Yeah, that's the thing I'm confused about. I suppose in the implementation, in the GitHub implementation, it should reveal how they do that. But
Well, if they're
Tell me
taking the
that.
average gradient, if the whole thing is to calculate the average gradient and then push that back through, maybe they don't. It's not in parallel. They're both contributing to the arrows, which is
right.
if they're doing two passes to figure out how bad you are, and then figuring out how bad you are is one number, and pushing one number back through. You
Oh, okay.
update in parallel. You update with contributions from both.
I don't think it's necessarily. I think it's just you've got a set of numbers which are data points, and you've got a formula to how to make a number out of that, which is the loss.
Right.
So you've got variables. So okay, some of the variables are split into two sets.
And you can
So you
just
calculate the derivative with all the forwards or backwards, whichever,
Yeah.
and then you substitute the values in. The fact that they're split into two separate classes, okay, it changes the formula, the layout of the formula text. It depends on that, because
yeah.
all the first variables appear in the L data and all the second variables are in the LC. But when you're evaluating, you don't care, it's just plug in some numbers.
So is it possible that backpropagation only happens on one branch? Because another branch, it just doesn't make sense if you need to synchronize and the weights, and if you need to replace the weights from one branch to another, that means whatever it learned here, it just loses anyway.
What do you mean branch?
Like you have two different
Layers.
two different networks,
You do
and the
in
weights are synchronized.
you did in the diagram, but the diagram was like I thought was a way to think about it. The section we were just reading at the end of the paper talks about no, it's the same network, but you hold on to some extra data. You just get two batches of calculations.
Right.
And also the weight updates. In a GPU CPU setting, the weight updates actually occur in the CPU space.
Mm.
So the GPU just does the calculation. They don't update the actual numbers inside the GPU. They push the numbers out. The CPU then updates it in memory, and then on the next run, it loads that entire thing into the GPU again. So maybe it is just doing one single update to the model based on the derivative based on both losses.
But it implies each batch must be having some things from R and some from T, or some from R and all the ones from T, or something.
What do you mean by each batch? I mean, like when you do the training, you're always getting the reference data set and also the target data set at the same time, and you're getting these two outputs. I was just wondering if
You
it was.
can't calculate this piece until you get the data from both nuns.
Yeah, but it's batched, right?
Yes.
Sure, but you can, the batched output is just a collection of output, right? If you batch these things through it, you can gather up as many things as you want here and then run these things and just mush both result batches.
Yeah, so my question is just, so you've got these two sets of data. When you make your batches, how is it formed out of those two sets of data?
Oh, I think it's just. I'm not entirely sure because I don't remember reading it anywhere. I think, but the batch sizes are the same, equal. So if you get 4 images from the reference, you get 4 of the target. And if your target only has say 1,000 images, but your reference is 1 million,
You just reuse those.
you're just reusing your target over and over. And you could even randomize it. Supposedly, you could just randomize your batch each time.
Augment even now.
Yeah.
Cool. And we conclusion. More pictures. We should look at the pictures.
False positives. That's always interesting. Is it Trump?
These are
No,
not
it's Trump.
unusual
Too
American.
close.
So the fault one class problem of novelty detection where the class of interest is American flag. So
The left-hand side.
positive means weird, or it means not weird in this case.
Majority of false negative cases.
We're looking.
Normal.
It's general.
Positive is normal.
It's saying that
Okay.
something is positive means it is an American flag. So false positive means it was wrong. It thought it was an American flag and it wasn't.
Right. So that's a hat. That's an umbrella. That's a zebra. That's.
And Captain Puerto Rico.
But that is an American flag, isn't it?
Well,
Yes,
yeah, but
it is.
it's in the background. Are you classifying it as like?
I don't know, if it was a
Yeah,
capture and it would tell you, show me all the American flags, would you tick it or not?
It's a weird
That's
human.
That's a good question because I'd say there's fundamental ambiguity. Like, suppose you need to classify a picture between cat and dog, and you've got a picture with a cat and a dog. What do you do?
Yeah.
Can't do it.
If one is zoomed up closer than the other, then you think yes.
And there is. Oh no, no, you do actually see the stars in the top right corner. No, well, the flag's backwards.
Yeah, no, that's probably it. Yeah, chirology. So it's saying these are not flags.
Backwards
So
in the first one.
I don't see
Yeah.
it like
Good
that
point.
this time.
Fair enough.
yeah. So that's the American flag and the flag of
Nepal.
Singapore or somewhere.
Nepal.
Sorry? Nepal is.
Nepal.
And that.
It's an old flag.
That's a piece of the American flag, but it's a real zoomed in version where you're like
Is it?
just looking at the
Yeah.
corner.
Could be Puerto Rican.
Yeah, it's
We'll never know.
You can't really.
It
So
could
that's a
be-
weird one. Like, if that is wrong, why is this right?
It could be Liberia, you know.
Because it's.
And why? What's wrong with this? The hat. Because if you zoom in on the hat, you'll see the same image. More or less.
A human made these determinations. at the end of the day, right? The human makes the determination. So just
Yeah.
like we're looking at the speech with the flag in the background and going, that doesn't make any sense. And the other one's saying, this should have been marked as a flag, and we're going, yeah, but it's like it's a chunk of a flag.
The machines are going to look back on this and agree with Bender. Kill all humans. They're not very good image classifiers.
And I mean, you could even say that the hat is an American flag hat.
Yeah.
There's a whole interesting thing in American politics that comes up every now and then where there's some conservative who's going, you need to respect the flag, and then you find out she was wearing underwear made from the American flag, and that's apparently okay. And
It's actually against the law.
yeah,
To wear the flag,
yeah,
but people do.
people do, and on
Here
stage
too.
for
It's illegal in the
Here
United States.
too.
really.
No, I'm asking.
It's illegal.
No?
I don't think so.
Because everyone is like swimming.
No, it actually has
shorts,
in the
like
law
everyone is
of
Australian flag.
flag law, whatever it's called.
I think you're only
No,
allowed to be
there's no
patriotic
restriction
if
by-
you're doing it.
Wearing a
If it's on your thongs or like a beer, or like that's the only example for patriotism. Like a person who has an Australian flag like planted in their front yard, like they're deeply suspicious. Like, that's
Well, it's probably suspicious, but is it illegal?
What?
no, that's what I'm saying. If they're respecting the flag,
Okay.
I view them as dangerous. And
Oh,
I
okay.
would not approach. I would repress supervision. Yeah.
Since it's
Probably.
a guideline.
What is guideline?
The flag wearing thing
Yeah, okay.
he's looking at.
Here in Australia, right? Oh, in the US. So it's not
Yeah,
illegal.
we don't care.
In Australia. Yeah.
The only people who are nuts about the flag are crazy racist rednecks.
I don't know, some people say technically illegal.